in the last class, we looked at a very simple latch, which is basically a circuit building block, which will enable you to figure out if a certain differential input is greater than 0 or smaller than 0. Okay. Now, we saw that the latch also has got problems in the sense that there are offsets in the latch, and the offset is due to two factors. One is static mismatch, and this comes about because when you make two nominally identical devices on an integrated circuit, changes in process parameters, local variations which are random in nature and cannot be predicted a priori, will basically cause a change in the parameters of the MOSFET relative to another. And equivalently, this can be modeled to first order as a change in the threshold as well as a change in the beta factor. And typically, it turns out for the values we are interested in, the beta factor mismatch is smaller than threshold mismatch. So, at any rate, this basically causes a static offset in the latch in the sense that it will detect. Ideally we wanted a threshold of 0. So if the delta V was greater than 0, you want it to fire as a positive value. If the delta V was negative, you would want to fire a logic of 0. With static mismatch, what happens is that there is an offset which you do not know a priori, and also we saw that there is dynamic mismatch, and this is due to mismatched capacitive loads on either end of the latch circuit, okay, and or a big change in the input common mode voltage relative to the natural common mode voltage of the latch. Is this clear? Alright. And we saw that these offsets would be fairly large, and which means that if you wanted to use the latch as such, okay, you will find that a flash ADD converter made with such latches to have reasonable amounts of DNL and INL would have to have such a large full scale range that it is quite impractical to realize in practice. So the next question is, what do we do about? So, offsets. So this brings us to the topic of what is called offset correction. Basically, these are all these circuit techniques come under the heading of what do we do to go and fix the offset problem. Okay, as we all realize, the dumb way of correcting offset is to simply go on increasing sizes of the MOSFETs so that the effect of mismatch becomes smaller and smaller because random variations are averaged over a larger area. Okay, and intuitively it makes sense that when you double the device size, the standard deviation goes down by a factor of √2. Okay, but we saw that to reduce offset by simply increasing device size will blow up the area of the converter as well as increase the power dissipation, simply because the parasitic capacitance that has to now be driven by any circuit which was driving the latch has now sees a enormously increased capacitive load, right? And it costs current to drive capacitance, which basically will turn out to result in increased participation in the circuitry driving the comparators. All right. Now, so the basic idea behind offset correction is as follows. This is what we have for the latch, right? So ideally, this was say delta V or Vn, right? So the inputs are VCM plus Vn and VCM minus Vn, Alright. So if Vn was positive, we should get a logical, if I look at the difference between the nodes X and Y after regeneration, alright, it is either VDD or minus VDD after regeneration, right? So ideally you wanted something which was like this, which would just change sign immediately after 0, right? In practice, because of offset, it does not happen that way, and what you are getting is basically VDD times sign of Vn minus V off. Alright? So this brings us to an idea. So this is the ideal desired guy. That is the ideal desired characteristic. Okay? This chap here. Alright? But what we have is this guy. Correct? So can you look at it and tell me what one could do? I mean, what is the relationship between this curve and this curve which you can exploit? Pardon? Okay, one is to shift the, you can treat the curve in red, okay, or the ideal desired characteristic as simply a shifted version of the curve in black. Okay. However, this offset happens to be random and unknown. Alright, so we don't know how much to shift it by. Alright. So what do you think? So shifting is a legitimate answer, however, it doesn't seem to be a practical answer because V offset is not known a priori. What else do you think I could do? See, whenever you have something, you want to get rid of it, there are two ways, there are at least two ways of getting rid of it. One way is to subtract off what you don't want. Another way is of dividing it by a large number. Right? So can you now look at it and tell me what you can do? I mean, how can you interpret this curve? See, if I have this guy, okay, I want to get to this chap. Okay, let me go in steps here. I want to get that chap. One way of doing it is to shift the characteristic by some voltage, but as we just discussed, that's not practical because we don't know how much to shift it by. Okay, what else? How can you interpret this? Another way of looking at it is simply scale the V in axis. Correct? Alright? And how much should you scale it by to make sure that the resulting characteristic is actually like this? How much would you have to scale it by for the threshold to look like? By infinite value. Correct? Does it make sense? Okay. So great. So if I have to scale the input to the, so if I have to scale this characteristic, what should I do? What is it equivalent in hardware terms? What does it mean to scale the input axis? Yeah. So if I had this curve, right, this is Vn, and this is V out, alright, and this is some V offset. If I scale the input axis by some A times V in, right, what will happen? This should become V offset by. Does that make sense? Pardon? No, we are not talking about ADCs here. We are just talking about a single latch. You understand? Okay? Alright. So, okay. So, what does this mean? Instead of applying the input directly to the latch, what you want to do is multiply this by some gain A. Alright. So this is plus, minus, minus, plus. So the voltage here will be A times. So this is a differential amplifier. It takes the input difference and multiplies it by some constant gain A. Alright. So what should the output be? What is the absolute voltage on this node? It is? Yes, it is VCM plus A times Vn, and this is VCM minus A times Vn. Alright? It is not to be confused with, it is not A times VCM plus Vi and A times VCM minus Vi. It is the output common mode. Okay? The common mode remains the same, only the differential mode portion is amplified. Okay? We will quickly see, very soon we will see how to do this. Alright? But for the time being, I assume this block is there. In which case, what should I do next? Then I will go into this latch, alright, with all the clocks that we generated, right? So there is phi 1, there is phi 2, there is latch reset and all this other stuff, okay? So if the equivalent input referred offset of the latch is some V offset, the equivalent input referred offset is of the whole of this new contraction is therefore the input referred offset is the offset of the latch divided by A. And having an offset, having the gain A is actually quite straightforward because we know how to make amplifiers. Alright? So, thanks to this amplifier up front, we are able to reduce the whatever offset the latch has by this large factor A. Is that clear? Okay. Now let's see how we can go and implement the amplifier. Right? It's straightforward for us to say, yeah, there is an amplifier and it all works. But let's see what happens. So this amplifier which precedes the latch is often called the preamplifier. Alright? Okay. So what is the simplest differential amplifier that you can, what is the simplest contraption that you can think of which can go into that preamplifier? A differential pair is the simplest thing you can think of. Alright, so this is VDD, this is R, let's say this is 2I, this is VCM plus Vn, this is VCM minus Vn, this is the output, VO, P, let me call that, and what is the output value? VDD minus IR plus GMR times Vn, and in a similar fashion this guy is VDD minus IR minus GMR times. In this particular case, you can see that the input and output common modes need not necessarily be the, when there is mismatch in the latch, it hardly makes any sense to assume that these devices are perfectly matched. So you have two nominally identical resistors as well as two nominally identical MOS transistors, right? So if I argued that these transistors don't have any mismatch, then anybody reasonable would say, then why bother with those transistors, use these transistors in the latch instead. Okay? So clearly mismatch here is now a problem. We've eliminated mismatch from the latch by dividing by this gain, but hey, so you have a bandage and then you found that the bandage is broken, right? So you'll go and fix the bandage. Alright? So let's see what we do. So clearly, as I said, if there is mismatch in the MOS transistors, so the issue is now device mismatch in the preamp. Alright? So if these two devices are not identical and have the mismatch in thresholds, in other words, the threshold voltage of this character, okay, is slightly higher by, say, delta, let me call this V offset, V off, okay. So this is VCM plus Vn that you apply, alright. Internally unaware, you are unaware that there is some random offset. Again, please note this battery is not accessible. Okay, it's just a way to model the mismatch in the difference in threshold of the two transistors. Okay, so now what is this equivalent to? You can decompose this as a common mode error and a differential mode error. Can you comment on what happens to the common mode component? So if I change the input common mode, what do you think happens to the output? So this is equivalent to running the ideal diff pair, okay, with VCM plus Vn plus V offset by 2. Alright. I'm sorry, the common mode component is simply VCM plus V offset by 2 and VCM again plus V offset by 2. Alright. No, common mode. Oh, it is. No, the common mode, yeah, that's correct. Yeah. That's minus V offset by 2. And this is also VCM minus V offset by 2. Okay? And so this is the common mode equivalent circuit. The differential mode equivalent circuit is, of course, this for common mode, the incremental equivalent circuit is like this. For differential mode, the incremental equivalent circuit becomes like this, which is Vn plus V offset by 2, and this is minus Vn minus V offset by 2. This is R. Okay, this is the differential mode equivalent. So what can you say about the effect of the common mode component of the offset? The will be, minus V offset by 2 and plus V offset by 2. Now can you tell me what the effect of the common mode offset is? Nothing, right? Because you know that the output, if you assume that the tail current source is ideal, then a change in this common mode by a small amount doesn't affect the action of the differential pair at all. Okay. What about the differential mode component? So instead of amplifying just the differential input, which is 2Vn, you are basically looking at it is like having 2Vn minus, it's amplifying 2Vn minus V offset. Right? So an offset in the mismatch in the thresholds of the two MOSFETs results in an offset in the, is equivalent to having an offset in the preamp. Does that make sense? Okay. So device mismatch causes preamp offset. Alright. The same discussion can be had for mismatch in the resistors also. Okay. So if the devices were identical, there was no threshold mismatch, but the two load resistors were slightly different, then it's equivalent to, pardon? The output voltage will not be, the differential output voltage will not be 0 when the differential input is 0. If you had an ideal preamp, okay, the differential output must be 0 when the differential input is 0. But if the load resistors are mismatched, that will no longer be true. Great. So we now have the input referred offset of the preamp latch combo to be the offset of the preamp, alright, plus the V offset of the latch divided by A. Alright. But please note, however, that the offset of the preamp as well as the offset of the latch are random variables. And we assume quite conveniently that both are Gaussian distributed. Right? And clearly, since they are occurring in very different devices, the offset of the preamp and the offset of the latch are not correlated at all. Alright? Which means that the total sigma offset, okay, is nothing but, you can simply add the variances. Alright? So this is the sigma, the preamp whole square plus sigma latch whole square by S. Okay? So if A is made sufficiently large, we can see that a big part of the input referred offset of this preamp latch combination is simply from that resulting from the preamp itself. Alright? Does it make sense? So now we have to do something about this. Alright? So one idea is to say, pardon? Okay. If you have to reduce the input referred offset of this entire combination, then earlier you were getting killed by the latch, now you are getting killed by the preamp. Alright? One thing is to say, I am going to increase the size of the devices in the preamp. Alright? To make sigma preamp inherently small. But as we, just as in the case of the latch, this is also a losing proposition simply because to reduce the sigma of the latch by the preamp by a factor of 2, I had increase the size of the devices in the preamp by a factor of 4. Alright? And and so this doesn't remain is not an attractive solution. All right. So any other ideas or suggestions? And one simple thought you could say is, last time we got rid of the latch offset by putting an amplifier before putting a preamplifier before the latch, and we got rid of the amplifier, the offset of the latch. All right. So you can now say, okay, I want to get rid of the offset of the preamp, so I can put another amplifier in front. So what happens? Is there a problem with this, or is this does it solve our? So while it is true that putting an amplifier up front before this whole combination definitely reduces the contribution of the preamp, all right, at the input of the combination, all right, the input effort offset of that amplifier that you put in before will dominate the whole picture, and you're again back to square one, right? So going on putting gain without doing anything, because fundamentally mismatch is coming, offset is coming from device mismatch, all right, and in all these solutions we are not addressing the fundamental problem of mismatch at all. Okay, so what was occurring somewhere else is now occurring elsewhere. The problem which was occurring due to some one pair of devices is now occurring due to some other pair of devices, but since we have not really figured out what to do about mismatch, this problem will remain even if you try and go on extending the solution with many amplifiers. Does that make sense? So we need to now really sit and think a bit hard and see what it is that we can do to eliminate offset. Okay, so we can come back to an earlier solution, which was the following, which is, all right. So this was V offset. Okay, so if we somehow know V offset, then what can you do? So let's say, let me take a single-ended example. All right. So this is an amplifier. We will extend it to differential cases, the differential case very soon. But to illustrate the idea, this is an amplifier. All right. So this has got some offset. All right. So if I okay, so this is V offset. Okay, but this is the black box that you get. You do not have access to the offset voltage because it's on, right? However, if I did know the V offset, what would I do? If I knew that the offset inside was, say, I don't know, 40 millivolts, what could I do? So if this was say V in, V out is basically V in minus V offset times some gain A. Correct? Alright. So what would I do to mitigate the effect of offset if I knew what offset was? So if I knew what V offset was, alright, so this is my amplifier with offset. What I could do would be to not put V in directly, but okay, if I made this exactly equal to V offset, okay, then the output voltage will be, it will simply be A times V in, because equivalently this battery is counteracting this battery and offset is cancelled. Correct? So if I knew the value of V offset, it is quite straightforward to cancel it off, right? Because I can, magically generate, if I say I somehow have a battery with exactly the right voltage, I can put it in in the opposite direction and cancel off offset. Does it make sense? Okay. Now the question is, if I didn't know the offset, how will I go and figure it out? Okay. So I have an amplifier like this. Alright, and what should, so this is V offset, alright. So if I gave you such an amplifier in the lab and asked you to find V offset, what would you do? Pardon? Vary V in until V out is 0. So in other words, can you figure out a circuit solution? Okay, one way is to say ground the positive terminal, alright, and do this, correct? Alright, okay, so what is the output voltage now? It is minus V offset. Please go and think about, why this circuit makes sense. And I mean, here obviously you guys know the answer, which is why, it came out in a flash. But okay, but it is the basic idea is the following, right? You have this knob. What will you do? I gave you this box with 2 inputs and 1 output, right? And I told you at V offset, the offset of the the input output offset is from V offset. So what will you do in the lab? As he said, put a knob, put a differential voltage between the 2 inputs and go on varying the voltage, okay, and see where the output goes to 0. So this is nothing but a negative feedback loop, right? So if the output is not 0, I will, change the voltage, keep changing the voltage in the proper direction until the output eventually becomes 0. So if you think about it, this is exactly what you do. Alright? So what do you think my next step must be? So if I took the preamp, alright, okay, connected it in unity gain feedback like this, the output voltage, if this gain was infinite, then the output voltage would be minus V offset. We'll see what happens with finite gain later on, but for the time being, let's assume that the gain of the amplifier is infinite. So we did this and we found that the output of the amplifier settled to minus V offset. Okay, but what do we want? What do we actually want? We want the amplifier. So this is the original amplifier with offset. What we want is to insert a voltage like this, which is equivalent to inserting, this is the inherent offset of the amplifier, right? This is if you knew the offset, then if you put a battery also exactly of value V offset in the other input, then the total input offset would be 0. Does that make sense? Okay. So what do you want? You want the preamp, okay, but you want to operate the preamp finally like this. Okay? You understand? This is only the arrangement that you want in order to estimate the offset. Is that clear? Okay, I do not want to connect my amplifier like this. Why? This is not what you want to do in regular operation, because you want the amplifier to have a large gain. Only then it will reduce the effect of latch offset. Alright. However, to find the offset, you need to put the amplifier in a circuit like this. Okay? Does it make sense? And so the summary of the idea is the following. So first find the offset. Alright, and that is done by one thing you can do. As I said, this is just another way of redrawing the same picture. So this is the amplifier. So during the offset estimation phase, this is how I want to configure the amplifier. Alright, and the output voltage will be minus V offset. Okay? Alright. So, I mean, I have something like this. The output terminal is sitting at minus V offset. But the moment I remove this connection shown in red, the amplifier goes back to open loop and does its own thing. Correct? So it's not just enough to have this, we must hold on to this V offset voltage. So what do you suggest? You hold this voltage as on a capacitor. Okay, let me call this C. So the voltage stored on this capacitor is minus V offset. Okay? Does it make sense? Then what do you do? Come on people, think and let's now do this together. Conceptually what you want to do, don't jump to circuits, right? Because first important thing is to figure out what you conceptually want to do. You're in the lab, what will you do? I will first take my amplifier, connect it in unity gain feedback, then I put a voltmeter at the output, I will read minus V offset, so I will charge the capacitor to that. Then what do? I remove the capacitor, right? So now this V offset is now stored on the capacitor. So what should I do now? So what I need to do is to add this capacitor, add this battery which has the offset voltage. Okay, let me make the bridge deliberately. Okay. So I need to add offset to the input, right? Adding voltages means connecting them in series. So if this was please note that this was negative relative to this plate. So I should connect the capacitor this way, alright? And okay, and now this gives me A times, this is conceptually what you want to do, okay? And if you want to reconfigure connections around an amplifier, what do you want to use? Yes. You have to use switches, okay? So combining these two pictures, right? So during some phase phi 1, let me call this phi AZ. Okay, I'll tell you why it's called AZ a little later on. Okay, so during phase phi AZ, the op amp is configured in this unity gain position. Okay, and this capacitor is also configured. This capacitor is the guy who holds the offset, right? Okay. should I do to the input? Actually, let me just, because the input comes on the left side, please note that when AZ is on, this whole thing is the same single node, right? And anyway, the input typically comes, you used to drawing diagrams with the input on the left and output on the right. So I will this is phi AZ. Right? So when phi AZ opens, what is the voltage on the capacitor? The voltage on the capacitor at the end of phi AZ is minus V offset. Okay? Then what should I do? I need to connect the V into the bottom plate. Right? So this is phi AZ bar. Alright, and this is V. Okay? So when I redraw this, this is phi AZ, this is phi AZ bar, this is C, this is Vn. What happens? This must be phi AZ. Does it make sense? Okay. Alright. So during phi AZ, this path is on, so the amplifier is in unity gain feedback. The voltage at the output of the amplifier, which happens to be minus V offset, is held on the capacitor. Okay. Then, after you're done, you need to lift off the bottom plate of the capacitor from ground and connect it to the input instead. So AZ, this whole process of cancelling offset is often called auto-zeroing. Okay. Which is why it makes sense to call this phase phi AZ, which stands for auto-zero. Alright. So basically what is happening during, if you have to actually correct offset, you have to measure it, alright? Okay? And measurement takes some time. So to measure, you need to reconfigure the preamp in some fashion so that one of the voltages naturally happens to be V offset. Okay? Grab that V offset and store that on a capacitor. Right? And once you've stored it on a capacitor, now you know what the offset is. So it's equivalent, and we know that if you don't draw any current from a capacitor is the same as a battery. So all that we need to do is connect the capacitor in the proper orientation. Alright? And you will find that you have cancelled the offset of the. Okay. The question is, the obvious question here is that if we did this for the preamp, why can't we do it for the latch? Okay. So anybody wants to take a shot at the answer? Yeah. So please note that the characteristic we drew for the latch, right? Something like this is the input at time t and the output at time. What is the input to the latch and what is the output of the latch? The input is very small, okay? the output is either plus VDD or minus VDD if you take the difference between the two voltages. But are the input and output being referred to at the same time? On the x-axis is Vin of some time t naught, right? What is so the output voltage is that corresponding to some of the time, because you need enough regeneration time to be able to resolve that small input into a large one. You understand? So, whereas in the preamplifier case, when I draw V in versus V out and show a characteristic like that, what do V in and V out mean? They are at the same time. Okay? So, which means that you can use feedback and you can use all this other stuff to find what the input is, what the offset is. Does this make sense? Okay. The peculiarity of the latch circuit and the way it operates, because it's a regenerative positive feedback affair, makes it impossible to find the offset using a straightforward technique like this. Alright? But if you wanted to find the offset of the latch, what would you do? If this was I gave you a latch and I said go and find the offset, what can you do? What all can you think of? Yeah, so one straightforward way I can think of is put a slow ramp all the way from the maximum negative voltage you expect to the maximum positive voltage you expect. Okay, and this ramp must vary from minus whatever VDD to plus VDD over a very very long range, so that many clock cycles exist in this whole thing, right? So ideally, when the input ramp crosses 0 is when the comparator output must toggle from a logical 0 to a logical 1, right? So if there is some finite offset, what will happen? It will toggle at some other clock cycle. You are expecting it to toggle exactly at say some nth clock cycle. You can, it will actually happen at some other clock cycle. If you know the slope of the ramp and if you know at what time it is toggled, you will be able to figure out what the offset is. Does it make sense? Okay. So there are people who do this, but this involves, as you can see, a lot of time first of all, as well as a lot of digital circuitry, right? So you need counters and all this other stuff. But this is also done in practice. Okay. When it becomes difficult or very expensive to have in power terms to have a preamp, because please note that the preamp draws static power. It's always carrying a current 2I, whereas the latch only draws power during switching. So if the frequency of this operation is very very low, it doesn't make sense to go on burning current. Okay, some strategy like that probably makes more sense. So I will stop here.